Dr. Harish, and all the dear participants. Let me welcome all of you for this second in the line session related to online course for school teachers, SETU 2025, Space Educators Training and Knowledge Upgradation Program 2025. So under the theme of space technology and applications, I'll be covering the topic related to communication and navigation satellite systems as well as its applications. So, because I have around 50 minutes, but I'm notorious for not keeping my time. So, if you feel bored, please stop me. I will request Dr. Harish to stop whenever he feels that it is time to now stop the thing. Otherwise, if all of you are ready, then we can start the session today related to communication and navigation satellites. So I'll share my presentation. Is it visible?
Yes, sir. Very much it is visible, sir.
Yeah, communication and navigation satellites and their applications. So let me begin my talk. Once again, welcome all of you. Now, communication. He said that it is called communication paradox. That is, Dr. George Bernard Shaw is very famous English philosopher. He used to say that the single biggest problem in communication is the illusion that it has taken place. So I will speak something or I will try to communicate something, but I don't know whether you have received it properly or what you have understood the way I wanted to convey. So that is the biggest problem in any communication, whether it is a technical communication or any other communication, even when we speak different languages. So major problem arises because people don't understand what the other speaker is trying to convey to us. So this is to be kept in mind whenever we discuss the topic of communication. And other thing, always used to quote this Alan Greenspan. He was the ex-president of World Bank. Some of you may be aware of, because all of you are teachers, so you may be aware that he used to say that I should warn you if I turn out to be particularly clear, you have probably misunderstood what I have said. That means he used to convey that I never speak in straight terms. So if I speak something and you feel that it is totally understood, then there is a problem. So that is what his way of conveying the things. Anyway, we start with this. Before that, we start the real topic of communication and navigation. I'd just like to introduce you. Kiran Kumar sir would have already given you the basic background about India space program. So I will not take much time. Dr. Sarabhai, who was the father of India space program, incidentally, he belonged to the place where right now I'm sitting here at Ahmedabad, that is the Space Application Center. So Sarabhai was father of India space program. He gave the vision and the mission for India space program. On the screen, you are seeing the house of Dr. Sarabhai, that is called Retreat. So he started working from his house, like initially, after completing his PhD from Cambridge University. Initially, he started working, doing his PhD there. Then World War came, so he came back, completed his thesis under Professor C.V. Raman at Indian Institute of Science, Bangalore. Then once World War stopped, he again went back to Cambridge and submitted his thesis, and that way he earned his PhD in cosmic rays related studies. So that was the beginning of India's space program. And as I said, he started working from his house, and then he invited Dr. C.V. Raman to come to Ahmedabad and lay the foundation of the cradle of our India space program, that is Physical Research Laboratory, Bhautik Anusandhan Prayogshala, PRL, from where our space activity started. So here you are seeing the pictures of Dr. C.V. Raman. Then after starting his work from his house, he moved on to this MG Science College near Gujarat University, where he had 2 rooms or 2 laboratories and started doing his experiment in these laboratories. So initial work he did there, because the PRL building was just getting built after the foundation laying by Dr. C.V. Raman. And then when it was ready, Jawaharlal Nehru, then Indian Prime Minister, so the work started from November 1947, and it was finished in 1954. So 54, Sri Jawaharlal Nehru sir came here and inaugurated the building of this physical research laboratory. So that itself shows the importance given to space program right from the beginning days, and with towering personalities like Sarabhai and others. taking care of India space program. Naturally, the importance you can imagine when Prime Minister comes to inaugurate this physical research laboratory. So this is physical research laboratory. And these are the pictures, as you can see on your screen. Dr. C.V. Raman laying the foundation of PRL. Then he's also laid the foundation of another community science center here nearby, near Gujarat University. And the last picture you are seeing is Dr. Santi Swarup Bhatnagar, about which you would have heard a lot. There is Santi Swarup Bhatnagar award in his memory given to young scientists. Then there is Dr. Homi Baba, then Professor C.V. Raman with Vikram Sarabhai. So these four great personalities, a rare picture of the four great scientists of different fields discussing together something at one place. So this is a very rare photograph, as you can see on your screen. And as I said, Sarabhai gave the mission of India's space program. He used to say that if we want to use space research for the benefit of common man and society, that was his motto, that we want to use space research and technology, it is for the benefit of common man and society. And after that, he has told something which I have hidden actually. He used to say that we are not here to compete with advanced countries to go to moon or Mars or put man in space. So, and today, most of you know that we are doing Chandrayaan, then earlier we did Mangalyaan, now we are doing Gaganyaan. So you will feel that whatever Sarabhai said, don't do it. We are doing that only. But that is not correct. When he said this, that was very early days. And today we want India to be a superpower, if not superpower, at least a regional power. And acquiring such technologies like Chandrayaan or Mangalyaan or Gaganyaan, putting man in space, these are also required. But I would like to clarify that these are all missions about which there is a lot of excitement among the students as well as children as well as people or everybody in this country after the success of Chandrayaan 3 and earlier Mangalyaan. Uh, this is only 25% of activity which ISRO does. That is Chandrayaan, Mangalyaan, Gaganyaan. This only forms the 25 to 30% of our activity. Rest 75% of activity is related to what we are going to talk today: communication, navigation, then remote sensing, and many other things. So only Chandrayaan, Mangalyaan, Gaganyaan, this is not the full story of ISRO. ISRO's story is somewhere else, as I can tell you. Uh, of course, Sarabhai died very early. All of you know that at a very young age of relatively 52 years, from 1919 to 71. And then Indira Gandhi was searching for a able successor. She zeroed down on the other gentleman, which you are seeing in the screen, Professor Satish Dhawan. He has just returned from USA then in 71 after completing his MTech and PhD from USA. And he was a mechanical engineer and he was appointed director of Indian Institute of Science then. Then Sarabhai died, so Indira Gandhi requested him to take over ISRO. He said that he wants to work for ISRO, but he doesn't want to leave academics because he was the head of the Indian Institute of Science then. So he wanted to do teaching also, academics. So there was a stalemate. Then the way was found out that ISRO's space program, which used to get run with informal headquarters at Physical Research Laboratory, PRL at Ahmedabad, it got shifted to Bangalore because Satish Dhawan wanted to remain in Bangalore, handling both IISc as well as ISRO. So that way, what was Bangalore's gain was our loss, that is Ahmedabad's loss. So we still lament that decision that our headquarters got shifted from PRL or Ahmedabad to Bangalore. But that was a correct decision those days because Professor Satish Dhawan handled ISRO for almost 13 years after that. Some of you have seen Bangalore IISc and headquarters. They are just opposite to each other. Only a road separates ISRO headquarters from Indian Institute of Science. So that is the reason that Professor Dhawan, who was heading both the institutes in those early days, Dr. Kalam, all of you know, the other person on the screen. So I don't have to tell you much about him because he was in ISRO for almost 25 years. Then he moved to DRDO, Atomic Energy. Then he became a scientific advisor to Defense Minister, then scientific advisor to Prime Minister of the country. And then he rose to become the president of our country. So that itself shows the capabilities. He was our rocket man, missile man, all type of rocket technologies he developed. So he was a very great technologist that all of you very well know. And apart from that, he was a great motivator when he used to speak and communicate. People, especially students and young scientists, get motivated by his speech, by his motivational communication. So that was the Dr. Abdul Kalam. Surprisingly, his tenure at ISRO was full of failure because those were initial days for rocket development. Of course, my friends will tell you much more about the development of rocket and rocket technology in the country, which was initiated by Dr. Kalam. So I will not dwell too much on that. But even though the foundation he laid, despite all these failures, that has led to the success of India's space program. So what we are seeing today, ASLV, GSLV, all these things, the success of that is mainly because of the foundation laid by Dr. Kalam. Bottom below, you are seeing another scientist in a jabba. He is Professor Yashpal Sharma. He used to be known as Professor Yashpal. All of you know he used to come on television under the Turning Point program, where he used to answer various difficult scientific questions in a very simple way. So his biggest asset of Dr. Yashpal was that he was a great communicator. Very complicated scientific problems or questions also he will answer in such a simple way that everybody will understand the basic fundamentals of the science principles. So that was his biggest hallmark. And of course, he was a great communicator. He was a social scientist. He used to work as a physicist in TIFR, Bombay, and then Space Application Center, from where I am talking to you, all of you today, which was set up by Dr. Sarabhai in Ahmedabad after PRL. So that time SAC was scattered all across Ahmedabad. Some of us were sitting in some college premises, some were sitting in some school premises, some were in some residential building and all that. So all were brought under one umbrella called Space Application Center, अंतरिक्ष उपयोग केंद्र, जहाँ से मैं अभी आज बात कर रहा हूँ आप लोगों से. So this SAC was formed in 1972. We just completed 50 years sometimes back. And Professor Yashpal, who was then working as a scientist in TIFR Bombay, he was brought as our first director. पहले निदेशक हमारे स्पेस एप्लीकेशन सेंटर अंतरिक्ष उपयोग केंद्र के प्रथम निदेशक प्रोफेसर यशपाल जी थे. And I am the 13th director. That is 13 is a very lucky number for me. And below right hand side, you are seeing a rare picture at Thumba laboratory, where you are seeing Dr. Sarabhai and the other young person, slightly blackish looking. He is Dr. Abdul Kalam those days. So these were the pictures of old days. And those days, PRL, that is Ahmedabad and Thumba, they were the two happening places as far as space activity is concerned. So this is how our space program started. And Sarabhai used to say that if you want to use space technology or do space research, first you should know how to use space technology for applications. So this is how currently today our Honorable Prime Minister Modi Sahab is putting a lot of emphasis on applications, उपयोग. तो स्पेस के उपयोग कैसे करें. So आप लोगों को भी ये सब हम ज्ञान दे रहे हैं, space education. That is because we want space to be used by everybody. For every common man in society, it should be used. तो उपयोग पे अभी काफी बल दिया जा रहा है. तो same way Sarabhai, when he started our space program, incidentally he gave a lot of emphasis on applications. So that is how our program started. As you can see, those days initially we launched the rocket, the Nick Apache rocket, which was gifted to us by France, and we learned how to fire a rocket or launch a rocket. So that was done on November 21, 1963. आपने देखा होगा कि इवन दिवाली में भी when we try to, our children try to fire a rocket, it goes here and there everywhere. So if you don't know how to launch a rocket, for that you have to learn the technique. So that is how we learned how to launch a rocket. That was the beginning at Tulls in Kumba. And then we learned how to use a satellite to beam a TV program, that is broadcast a TV program, which is received by all across the country. Similarly, communication experiment STEP, so that was site, that is satellite instructional television experiment site. We have just completed 50 years of site this year. and we are going to celebrate in a big way. Similarly, STEP is a satellite telecommunication experiment project where we learned how to use satellite to do two-way communication. That is doing voice communication, data communication, and all type of communication, one way, two way, all these things. And then in PRL, the experiment related to remote sensing was initiated by another great scientist, Dr. T. Pisaroti. He used to work on the various remote sensing experiments, and he used a balloon or a helicopter and aircraft to find out the disease in a coconut tree from a remotely engineered platform. That is helicopter or balloon or aircraft. He used to watch the coconut trees and then get the pictures of that and try to find out through remote sensing what is the disease affecting this coconut. So this is how we used applications to learn about the space research. And this was right, as I told, a great thing about this was 2,400 remote rural villages. We had a American satellite, ATS-6, a transponder on ATS-6, and 2,400 remote villages we set up at the community center. The various TV sets were set up all across the country in 1975-76 time frame, and a program was transmitted using satellite. Some of you will say that what is so great in that? Today, sitting at our home on your mobile, you can as well watch a TV. But what was great was that you can remember that it was time 1975-76 when even electricity was not there at many places, and we connected 2,400 remote rural villages. We selected all these villages and set up these TV sets in that community science community centers, and that way all across the country, 2,400 villages, they received this TV program and watched it. So it was the largest mass communication experiment ever carried out in the world. So that is how our program started, with these experiments of doing applications using satellite. Similarly, communication experiment I was. And today, if you see, the global space market is $370 billion, and in that India's share is 7 billion. That is roughly it will be around 2%, not even 2%. By latest survey, it is 1.7%. So Modi Sahab wants that now more and more people should be brought into the space sector. Earlier, space used to be a very closed affair with only government organization like ISRO working related to space. But now government wants that private sector should get involved, academia should get involved, teachers and students also get involved, student startups should come up. So all these things are happening now to increase the share from 1.7 or 2% to at least 5%, if not 10%. So that is the idea with which our Honorable Prime Minister has opened up the space sector. And for that, we have now set up this one public sector unit, New Space India Limited, where it was given 2,000 crore rupees as the initial funding with which it has to sustain itself. And all ISRO projects will be now done through NCIL. And similarly, a arbiter or a facilitator was set up that is called INSPACE, Indian National Space Promotion and Authorization Center, which will work as a arbiter like TRAI, Telecom Regulatory Authority of India, something similar to that for space activity. And it will also work as a facilitator. It will support student startups, give funding to them. It will also support private sectors or non-government entities, as it is called NGE. New space policy has been brought up now, 2023 government. Our cabinet approved the new space policy. Along with that, communication policy, navigation policy, geospatial policy, all these policies are now in place. A space data policy has been set up with which now everybody can receive the data from our remote sensing satellites free of cost up to some level. So all these new things are specific things to encourage space activity in the country has been set up, and the SETU program is also part of that space related activities, outreach and training, under which we will like to educate, sensitize all of you people like students as well as teachers, faculty members all across the country, so that the space activity proliferates in our country. This is our record. Last 55, 56 years, we were set up in 1969. So we just completed 56 years, 15th August. So around 231 missions we have already completed, as you can see. And last mission was a failure. All of you know that. So although this chart looks very promising or very satisfactory, why I mentioned about failure is because our last launch, even after so much success, the last launch was a failure. So space is a risky business. That all of you should understand that we are not assured of pure success. So if today we are successful, tomorrow same rocket may fail also. So that is the biggest risk involved in any space mission. You must have heard about SpaceX or NASA also failing in many of its missions. So like this, space is a full of certain uncertainties, as it is called. But overall, our record is very satisfactory, as you can see, and we have very good missions, and we have our own rockets about which you will get to learn more about during this lecture series. Then about satellite program also you will learn, and today we'll concentrate more on the navigation and the communication. So this is the place where I am sitting right now. This is Space Application Center, Antariksh Upyog Kendra, Ahmedabad. It is located in Ahmedabad, and what you're seeing on your screen, the big antenna along with some dome-like structure, this is India's first communication Earth station. What is a communication Earth station? It is a Earth station which communicates with the satellite, which is in the orbit at 36,000 kilometers. So through this big antenna, which is a 14-meter diameter antenna, this Earth station was built as a contract which Sarabhai gave to a Japanese company called Nippon Electric Company those days, NEC. Today it is known as NEC from Japan. So they built this particular antenna and the Earth station, and it is India's first Earth station. And this was the only building in all this total area from Gujarat University onwards. Some of you are familiar with Ahmedabad. So everything was a jungle or a forest, and in this first building came up. And today we have 50 buildings in this place where I am sitting right now. So in my campus here, main campus, and we have two more campuses. Right hand side, you are seeing this new Bhopal campus and a Bhopal Technical campus. So they are located around 7 kilometers away from the place where I am sitting right now. So now we have three campuses in Ahmedabad. We have very good Vikram Sarabhai Space Exhibition, which is open even on Saturday, Sunday. If you do visit our exhibition center, we, as I said, InSpace was set up with Ahmedabad as headquarters in one of our Bhopal campus. So we have given space to them. They have set up their office and laboratories there. And left side bottom, you are seeing the technical complex built for InSpace and with our support, where a lot of facilities have been set up where teachers or faculty members like you, academia, then students, startups, all these people can come here and work free of cost and very nominal cost for some of the people. And private sector also can come and work here. So we have set up all facilities. Now you don't have to worry about the test facility and other things that will be provided by us, by ISRO, by InSpace to all of you who can want to work in space. And right hand side bottom, you are seeing another Earth station called Delhi Earth Station. Again, it has a heritage value. It was the place from where Indira Gandhi used to address the whole country. So even those days, Prime Minister has to go to this place to address the whole country. Today, sitting at your home through your mobile, you can do video conferencing or video talk with anybody in the world. But those days, even Prime Minister has to come here to address the whole country. So this is SEX activity, payload, and application. So rocket, satellite, all of you know about that, and you will know much more about as the lecture series progresses. But I want to tell you about the payloads and application. The payload or the sensor or the instrumentation, it is the heart or the brain of the satellite. So see, rocket works only for 15 minutes. It puts the satellite into the right orbit. The satellite is the platform which provides you the power supply, and it provides the stability of the platform and other things to the instrumentation. Well, the sensor or the payload or the instrumentation is the actual thing which does the work after the launching of a satellite for next 1, 3, 5, 7, 10, 15 years. Up to 15, 20 years also we have satellite working. And the working means these instruments which are there on board satellite, payloads, midbar, they do the work actually. So we have communication and navigation satellite about which we'll be talking. Then we have optical camera system, and then microwave remote sensing radar systems. So these are all the payloads. And we also do the application part, the end product, उपयोग. So finally ये सब हम कर रहे हैं किसके लिए? कि उपयोग करने के लिए. Satellite technology, research, everything is being done so that all of you can, or all of us can use this. So these applications are also done here at Space Application Center, Antariksh Upyog Kendra, Ahmedabad. So as you can see from the human resource breakup of my center here, we have mechanical, electronics, computer engineers, we have lot of science people, geoscience, biological science, physical science, chemical science. So all of you science and maths teachers who are listening to this program, almost all similar people are there here with me, working here as scientists, as mathematicians, as engineers. So if you can see our breakup out of the 2,000 people which we have all type of people, all type of expertise is there. So we are more, in fact, like a academic institute or a university rather than a government institute. And we do all type of activity, as you can see, design, development, realization, application development, software development, technology development, and capacity building, training, all this type of activity we do here at SAC. So SAC is one of the most unique center of among all ISRO centers. It is unique one because no other center has all such similar variety type of activities. And we work with industries, we work with SME, MSME, academic uh, people like you people with various universities, colleges, research institutes, as well as space agencies. So this is how we are structured. And now coming to our topic, birth of satellite communication. All of you have heard about Arthur Clarke, Sir Arthur Clarke, who sitting in his laboratory, he used to work in Sri Lanka. He say he did some mathematical calculation, like some of the teachers like you, and he calculated and said that if we put one satellite or three satellites all across the globe, located 120-degree apart, that is three satellites across the whole world, they will cover the communication over the whole world. That is, one satellite can cover 1/3 of the world. So thanks to a few tons of electronic gear, 20,000 miles. 20,000 miles is equivalent to roughly 36,000 kilometers. Above the equator, ours will be the last century of savage, and for all mankind, the Stone Age will be over. So he said this will be a revolution. This is just his prediction sitting in his lab, that if you put this type of satellite at 20,000 miles above equator, we will come out of the Stone Age and we'll enter the new era or the modern era. And that is what finally happened. First artificial satellite, all of you know, Sputnik was launched in 1957 by Russia. Then first communication satellite, Telstar, was launched by Bell Labs in 1962. Again, it was a low Earth orbit satellite, and first geo communication satellite, the one which is at the 36,000 kilometer, because from there anything you put at 30,000 kilometer orbit, it will appear stationary with respect to Earth, because it will move with the same speed as the Earth speed. So that's how it was the first geo communication satellite in 1964, Syncom 3, which was put by Hughes aircraft system those days. So these were the initial days of satellite as well as communication. And this was what Dr. Arthur Clarke predicted, that three geo satellite can give instantaneous global coverage as far as communication is concerned. If you put three satellite located 120-degree apart, you can cover the whole world for doing communication. Of course, after that, everything emerged. There were LEO satellite, there were MEO satellite. These were geo satellite mostly used for communication. So this is how the history of communication started. And as you can imagine now, a satellite-based communication system will consist of space segment, that is the satellite in the orbit. Then there will be ground system, that is the Earth station, which I showed you. So that is also required to communicate with the satellite. Many times satellite drift. So we have to correct the orbit of the satellite. So all these things is helped by this ground system or the Earth station. Then there is a communication channel. Then in between satellite and Earth station, there will be atmosphere and free space. So that will work as a communication channel through which the various microwave signals will pass through from satellite to Earth station and vice versa. So this is how the activity happen. I will not go into too much detail because the pictures already tell you the story. So this way we have various Earth stations. They will communicate with the satellite, and this way two-way communication happens. And then we have what we call fixed satellite service, that is provide continuous services with the other related to communication, which is related to voice or data, as the specifications. So these were our satellite which are doing the fixed satellite service. Then we have what we call mobile satellite service. Like you have your smartphone or mobile phone, which is used for communication between one person to another. Same way we can use satellite and use a satellite phone to do the communication from one place to another or one person to another using satellite as a intermediary in between. And then we have broadcast satellite services, about which I told you about the TV transmission. So we want to transmit a DTH program or the TV program using a satellite. So then you have DTH satellite, so direct to home satellites or satellites of different varieties. So this is how the activity happens. So this is how the broadcast satellite for DTH or TV transmission. So that is another application as far as satellite is concerned. And today, right now, we are using satellite for broadcasting TV, direct to home, networking, similarly communication from one place to another, two-way VSAT connectivity. There are other mobile satellite search and rescue. That is for disaster management. And then there is the development, education and communication program, which is used for generally telemedicine, tele-education and emergencies communication. Whenever disaster happen, the first thing which gets affected is the normal phones. Phones stop working. So that time only satellite communication help us to maintain the communication. So these were our initial days. Apple was our first satellite, as was already told. INSAT-1 series we started working on, where it was defined as the Indian National Satellite System, where we gave order for 4 satellites, which was built by Ford Aerospace USA. And this was awarded on a turnkey basis, where we took part in design as well as testing of the satellite. But the satellites were basically realized or built in USA by Ford Aerospace. Our engineers used to go there, work and take part in design as well as testing and evaluation. And then after learning during the INSAT-1 series, we started our own program called INSAT-2 series onward. So after INSAT-2 series and onward, we are now self-reliant. We do our activities on our own in India. So, and now we are launching the satellite also from Indian soil in Sriharikota. So now we call it a GSAT series. So this is how our program now appears. So INSAT-1 series, I already told, 4 satellites were ordered. Out of that, 2 worked and 2 didn't work, because the satellite design was very complicated. Apart from communication, we have put meteorological observation, or what we know as a weather forecasting terminals also we have put on this satellite. So there was a VHR radio meter, which was a part of this communication satellite. So that complicated the design of the satellite in such a way that the center of gravity of the whole structure of the satellite got displaced. So what we have to do, we have to use this, there is a boom-like structure you are seeing. So that boom used to balance the CG of the satellite, and that's how this satellite was evolved. And so it resulted into a very complicated configuration of the satellite. So due to that, there was real challenge in realizing and then launching this satellite. So 2 satellites worked very well, 2 failed. In one satellite, there was a power failure. In another satellite, the boom didn't open up. So the satellite went on tumbling and it was not operationalized into the right orbit. So that's how we lost 2 satellites at the beginning of our program. But after, as I said, our scientists learned a lot by going to USA and discussing, learning, taking part in the development of INSAT-1 series. So from INSAT-2 series, we have now started working on our own, developing our own satellite program. So this is how our satellite program, and as I said, now we call it GSAT program, because everything we do indigenously and we launch it also from our soil. Earlier satellite we used to launch either from French Guiana, taking help of CNES, that is the French Space Agency, or we used to hire a Russian launch, or we used to hire a NASA launch. So that's how we used to launch our satellite. But now onward, we are launching our own satellite from our own rockets, that is GSLV Mark II or Mark III. So that's how we call it GSAT series. So now we have a very thriving communication satellite program, and as you can see, the payloads are also of different varieties. They are in all frequency bands: C band, KU band, Ka band, MSS, high throughput, UHF band, and now we are moving to higher and higher frequency band, that is QV band, which is called millimeter wave band, and then optical frequencies. So we are entering into the era of optical communication, and now all of you would have heard about the quantum communications. I'm going to tell you about that also. So these are the different satellites which we built under each category: C band, Ku band, Ka band, and then similarly we have our own navigation program also. That I'll come to that separately. But we have navigation satellite in L and S band, that they have the transponders in these two particular bands, because L and S band are earmarked for navigation activities worldwide. So ITU allocates frequency in these L and S band only, where we have to use the navigation transponder. And then we have Gagan and our own NavIC or IRNSS payload. So that's how our navigation program is working. And if you see our scenario, it is, these are the all the satellites we have built over the years. Last almost 50 years we had been working on communication satellite. So the history of communication satellite is as old as the history of ISRO, because we started working on IRS remote sensing, optical remote sensing program, as well as the communication program right from the beginning. And in between we added microwave remote sensing, radar development program in remote sensing, and the navigation program as far as the communication activity is concerned. So this is all different types of satellites we built. And today we have around 250 transponder in different frequency band working and providing communication services all across the country. So this is how a typical communication transponder or payload will look like. It is basically a bent pipe transmitter where a transmitter is used to transmit the signal, a receiver is used to receive the signal. There is an antenna to receive and transmit the signals, and they pass through various filter banks and many other components. And finally, it will do the work of a what we call a bent pipe transponder, where there will be transmission as well as reception of signals from Earth and to Earth. And there will be a beacon transmitter which will be used to locate the satellite and to establish the link between the transmit and receive antenna. So that is how the overall simplified structure of any communication satellite look like. And these are all the different building blocks: antenna, then front end electronics, which is mostly RF front end. Then there is a receiver channelization, which will give us various number of transponders. Then there is a various, each transponder bank will have the power amplification and channel amplification circuitry. So that is known as power amplifiers. Either it could be a tube or it could be a solid state power amplifier nowadays. Then there will be need of various filtering and multiplexing and demultiplexing operations in transmit as well as receive chain. So this is how the basic building blocks, and mostly if you see, they are all consisting of mostly RF and microwave. So if you see, presently we are working on all these frequencies. Currently, we have already moved to this Ku and Ka band high throughput satellites, and we are now building very large satellites of weight 4,000 to up to 6,000 kg, and from power of 1.5 kilowatt to up to 15 kilowatt. So this is where we are today. And in future, as I said, we are moving to Q and V band. We are moving to optical frequency band, and now we are moving from geo orbit. These are all geo satellites, or satellite at the height of 36,000 kilometers, where they appear stationary with respect to Earth. And from there, they will move on to now what we call the LEO and the MEO satellite. So that is the change which is coming up all across. So these are some of the typical satellites which we built. The Sat 11 was our highest capability or the highest power satellite which we have built, with a lot of high bandwidth or high throughput capabilities. GSAT 20 is the latest in the series, which we recently launched through SpaceX. Then we have 6,000 kg total payload transponder capability, GSAT 17, 18. So these are all the various category of satellite which we have built. One example I would like to give you is GSAT 9, which we initially it was called the SARC satellite, where Pakistan was also part of that. Afterwards, due to various reasons, it went out of that particular cooperation. So we called it now the South Asia satellite. So it is dedicated as a India's gift. So Honorable Prime Minister Modi Sahib has given as a gift this satellite to various of our neighboring countries. So this is the one way of increasing our influence or the goodwill among the neighboring countries. So we allocated two transponder to each of our neighboring countries, including Afghanistan, then Bangladesh, then Nepal, Bhutan. All these were allocated to two transponders. So we have this network of almost 12 Ku band transponder to 6 countries. We allocated two bands. and the mission NavIC. So this was launched in 2017, and this is how our first high throughput satellite was built by us as a experimental satellite, where it will cover the whole India into multiple region along the beams, and the lift of mass was around 3,000 kg. So this was a precursor to our high throughput satellite, and afterward we developed, based on this experience gathered of GSAT 19, we developed the GSAT 11 satellite. As you can see, it was the highest throughput satellite which we have built till now. And for that, we have set up 4 Earth stations. Each Earth station has a duplicate site, what we call the DR site or disaster recovery site. Because if something happens to one Earth station, or during rain, if there is a rain in one place, the transmission gets shifted to the other Earth station. So that is the requirement of any communication, because we want to have a uninterrupted communication. So this is how the communication high throughput satellite series started. So this way it connected the whole country. It was divided into small beams, and they were all put together and integrated as a part of the GSAT 11 satellite. We have 4 major regional hubs to cater to this Earth station requirements, and each site has two Earth stations, where the RF portion was duplicated at 2 places. Similarly, we have these mobile satellite services, the GSAT-6, which contain a very big antenna, 6-meter diameter antenna. This is the first time we built such a big antenna for communication, and it was launched almost 10 years back. Now we are ready to work for a replacement of the GSAT-6 satellite, as we call it GSAT-32 satellite, which is going to be almost similar to this, where we have divided the whole country into 5 beams and use the frequency diversity to provide mobile communication from any region to other region. So like you use your normal smartphone, we use a satellite phone to carry out the communication from one region to another region. And this satellite is regularly being used for various NavCom applications, as I'll come to that. So these are some of the recent developments which we have carried out over last 3-4 years. GSAT 24 and GSAT 20 were our biggest DTH, as well as the high throughput satellites, which we have now launched under the new era of new space activities. Then there is IRNSS 1J and IRNSS 1K, which has been launched recently. In January, we launched NVS 02, but unfortunately, the satellite has not reached its right orbit. We are trying hard to raise the orbit of the satellite. So due to some malfunctioning, again, as I said, space is a risky business. Similarly, we have the GISAT-2 satellite. This is the first time we'll be doing a geo imaging from a geostationary orbit. So these are all the satellites, and we have made an experimental payload for spectrum monitoring payload, which is also has its use in electronic or signal intelligence activity, as well as we will be using it to monitor the air traffic. So we use satellite to monitor the movement of various aircraft all across the country in the Indian FIR region. So that is how the spectrum monitoring payload has been demonstrated, and now we are looking forward to a full-fledged constellation of ADSB type of network, which will do the regular monitoring of all the aircraft all across the country. The tasks which are right now performed through ATCs, that is localized way, but this ADSB will provide the overall connectivity. You may be surprised that almost 90% of communication happens through fiber optic networks or the terrestrial network, which are generally fiber optic networks. Even across the sea also, the fiber cables are being laid. So you will question that why we need satellite communication then. Satellite communication is very much essential because it works as a backup to the terrestrial network. So wherever any breach of service is there, automatically the satellite will take over the services. So that is the first requirement. Second is during disaster time, as I mentioned, the first casualty is this type of terrestrial communication, or terrestrial network will fail. So your phones will get dead. So in that scenario, only satellite communication will work. So this is one typical example during the Uttarakhand Kedarnath disaster. Immediately in 2014, our team rushed to Haridwar, Dehradun, Rishikesh, all these areas, and set up these VSAT terminals so that immediately we can restore communication with those places with anywhere in the country. So that way we could provide the communication service. So that was the immediate use of satellite communication. Similarly, same year, the Kashmir was flooded. Srinagar was totally underwater, as you can see here from this photograph. And immediately we rushed our teams to set up the VSAT terminal at Chief Minister's bungalow as well as the governor's house in Srinagar, so that immediately we can restore the communication between Srinagar and Jammu as well as Srinagar and New Delhi. So that way we can find out the situation at there, prevalent there, and then rush the various relief measures for this. So that is the practical utility of satellite communication during disaster time. And we have seen it, it came very handy during such disasters. And of course, as I said, it works also as a backup for the our terrestrial network. Whenever any problem occurs in any place all across the country, immediately the satellite services take over the activity right now done through the fiber optic terrestrial network. What are the trends now changing? So these are the satellite communication has become a routine affair. As I mentioned, you launch a communication satellite which is put at the height of 36,000 kilometer and with the transponders, as I showed you, with these building blocks. But now the trend is toward this type of what we call advanced mobile satellite. There is a need of heavy geo satellite. There is a need of LEO satellite constellation which will operate at the LEO orbits. Then there will be need of a flexible satellite. So I can configure this satellite the way I want. I can use it as a TV transmitter or a DTS satellite also, or I can use it as a communication satellite for doing voice communication or data communication or internet broadband services as well. So these are all the activities which we do now as a part of advanced satellite communication, and it has a flexibility that it will help us to even transfer the beam from one place to another. So steering of beam, then providing more services at the area where there is more traffic, and to provide more power to such locations like urban areas. So all these things are the essential activity of modern satellite, what we call the configurable satellite. And or now most of the satellite, when we started, as I mentioned, we started with INSAT 1 and 2 series, and now we are on to the what we call the high throughput satellite series. So in high throughput also, the trend is from high throughput to very high throughput to ultra high throughput. So this is just typical example of how the satellite generations even in high throughput satellite, which began with a IP star type of satellite in 2005. So in last 20 years, technology has evolved in such a way that we have moved from high throughput satellite to a ultra high throughput satellite. So this is how the overall configuration has been changed, and we have moved from, as I said, IP star type of satellite to Ka-band satellite to a Viasat 3 type of satellite, where a 3 satellite constellation can cover the entire globe to provide a 1 terabit per second sort of throughput as far as the internet broadband services are concerned. So the equivalent satellite which we have built in India is GSAT 11 as our first GSAT high throughput satellite series. Then we have last year and we launched the GSAT 20 satellite from SpaceX USA, and through a Falcon launcher. So that is providing a, what we call a very high throughput satellite services. And now we are on to a future satellite, which we are building first as a technology demonstrator satellite, TDS 1 and 2. And after that, we will move to the operational satellite, as I'll come to that. So this is how we are evolving as far as the activities are concerned in high throughput satellite, very high throughput satellite, and ultra high throughput satellite with our future GSAT series of satellites. So we move from 10 Gbps to now up to 1 terabits per second sort of communication. And as I mentioned, now there is a debate going on whether geo satellites are better for communication, or now the trend is more toward the LEO satellites, and I will come to that. So this is the scenario as far as Indian very high throughput or ultra high throughput satellite is concerned, where we are moving to KU and Ka band, and from there to Q and V band. The hubs are right now in QE band, and the user terminal will be in Ka band. And from there, we move on to even user terminals moving on to Q and V band. So this is going to be the key technologies as far as RF systems are concerned. We'll go for more and more miniaturized system and very high power system and very large satellite to build for that. And the Other thing is, instead of worrying more about throughput, it is called good put. We are trying to put as per the requirement. So we can have a single all India beam which can provide the TV transmission or TV signal to whole over India. Same programs can be received, or we can reconvert this same DTS satellite into a multi-beam coverage where it will provide the internet broadband services. So that is how the technology is changing. We'll have flexible coverage. We'll have on-demand distribution of capacity. So some urban areas like Ahmedabad, Bombay, Calcutta, New Delhi, which has high internet bandwidth requirement, we can divert our resources toward these urban areas. And rest of the areas where there is less demand, we can do away with the smaller requirements of throughput. So that way, we are moving on to this type of newer and newer technologies where large multi-beam reflectors, so very big size reflectors, 3 meter or higher, are used to provide communication from satellite to ground station. So like you see a big earth station on ground, we have a big antennas on the satellite itself. So this is how, in the same way, mobile satellite, as I said, moving from your terrestrial network to a satellite phone. And the day is not far when we'll have merging of the satellite phone and your smartphone, which is working on a terrestrial network. So this is our first mobile satellite, GSAT-6, which I mentioned. So it has a very big 6 meter diameter antenna. And this is going to be the advanced geo mobile satellite, which will provide the support for your smartphone. So your smartphone becomes the satellite phone. So this is how the technology is going to change, and how uh, the things are changing is that now we have Starlink, OneWeb or Kuiper type of satellite, which has very small satellite, low Earth orbiting satellite, and there are dedicated large terminals are required for that. And there are other type of satellite called uh, what we call the uh, ubiquitous mobile connectivity through large satellite. So you have a very large antenna on board the satellite. So this is a 8 by 8 meter square or 64 meter square. As you can see, these are number of people just standing across the this antenna, which is of the size 8 by 8 meter. And the terminal which we use to communicate with this antenna will be this small terminal like your smartphone or your satellite phone. And in other Starlink type of satellite, we have a slightly bigger terminal called VSAT terminal, while satellites are very small. So this is how the things are changing. So the challenges are how we can have both the type of satellite existing together. So LEO broadband satellite communication is going to be the new future, and already all of you are hearing a lot about Starlink satellite, which is providing service all across the world. We have our own OneWeb satellite, which is bought over by Sunil Mittalji of Airtel Prem. It was actually a UK satellite series, which has been taken over by now Airtel under that conglomeration. Then we have Elon Musk Starlink series of satellite, where he has already launched around 6,200 satellite, and he has planned to put almost 20,000 satellites. These are around 780 satellites are planned under OneWeb. Similarly, Telesat is another series. So like that, Amazon services, everybody's coming up with their own satellite. And there is, we are going to recently launch Bluebird 1, Bluebird 2 satellite uh, under the Blue Walker series, where it will provide the mobile connectivity to with your smartphone. So already experiment have started in USA to provide mobile communication on your smartphone through this Blue Walker type of satellite. So this is how the trend is changing. And the importance of this LEO broadband satellite is that they operate at very low Earth orbit, around 500 kilometers, around that, 500 to 1,000 kilometers. And one typical example or utility of this satellite is that Russia-Ukraine war is going on since last 3 years. Russia has bombarded Ukraine like anything. So everything is destroyed there. All the TV towers, the telecom towers, everything. But still today, TV is working in Ukraine, internet is working in Ukraine, thanks to this Starlink series of satellite where Elon Musk is providing free service to Ukraine. So that is the power of the satellite broadband services through LEO satellites. So that shows the importance of this type of satellites. We have also worked out a constellation of around 140 satellite. Of course, it will not take care of whole India, but almost 60-70% of the urban area coverage is taken care of by this constellation. It will operate at around 1200 kilometers. So we are looking, government is now looking forward to a PPP mode implementation of this particular configuration, where jointly government and private sector will build this 140 satellite, and which will provide the Starlink type of services for our own country. Of course, once you have LEO orbiting satellite, it can provide services anywhere across the world. There is no boundaries as far as satellite communication is concerned. Once you put the satellite in LEO orbit, if you have a geo satellite, it will cater to a specific area because it is stationary with respect to that particular country. So it will coverage will be limited to that region only. While unlike that, LEO satellite will be always moving satellite. So you have to, that's why you have to launch large number of satellites. So this is how the technology we have evolved. Of course, Reliance initially showed some interest, but again now government is still looking for a partner uh, to ISRO who can do this activity and also fund this program, because government alone is not ready to fund this particular program. But of course, we may think of a dedicated program for our strategic sector, but these are all decisions taken as per the needs of the country. But we are ready with the technology as well as the configuration. And as I mentioned, the similar LEO's technology can be used to provide the air traffic control services, ATC services, and movement, recording the movements of the all the aircraft which are under the Indian FIR region. So this is how we had experimental payload across one of the microsatellite, and now we are going to expand it to include large number of almost 45 to 65 satellite will take care of the overall communication or the movement of air traffic across the Indian fly zone region. So that is how it has been all planned out. Again, we are looking forward to a PPP mode of operation where Airport Authority of India, ISRO, and one more private partner could be working together. And now the trend is towards, we already saw the trend changing from geo satellite to LEO satellite. And now the change, another change is coming is the technology change. That is, we are now using what we call software defined satellite. You know, software is used to be build a reconfigurable system. So similarly, now you can control the working of a satellite sitting here on Earth by changing the software inside the satellite. So that is how the trend is. So I can generate a beam which will cover the whole country, or I can generate small beam which will cover specific areas. So that way I can reconfigure the software on board the satellite from the sitting here on Earth by sending the appropriate technology or the signals across the satellite, and it will get reconfigured to from a single beam communication satellite to a multi-beam configurable satellite with a, what we call a mobile satellite service or fixed satellite services or internet broadband services. So like that, it is possible to do digital beamforming to do the configurability, and it all everything will be defined by what we call a network management system, which will be part of the user segment. So user can configure the satellite the way it wants, and that is going to be the trend nowadays. Similarly, various IoT sensors which are there collecting various data, so they also can be integrated through the satellite-based IoT services. So this is the another change coming up. This Blue Walker, I already told you about. Starlink satellites, again, they experimented using a smaller Starlink satellite to provide the smartphone communication. So, and Link Channel is another satellite where they check these GSM protocol. So using a smartphone to provide communication, internet broadband and other services to the user. So this is going to be now technology. So this is the revolution which is going to happen where automatically your smartphone gets converted to a satellite phone. See, today when you go from one place to another, we always feel very embarrassed when we don't get the network coverage on your mobile. But that will be thing of the past. Your mobile smartphone will automatically get converted to sat phone. So you don't have to worry about the absence of network coverage. So this is how the technology is moving with Blue Walker 3, Omnispace. So all these things are working together. In India, we are also working with IIT Hyderabad using that chip which they have developed what we call a NB-IoT waveform. narrowband IoT waveform, which will have a common heritage all across the terrestrial network as well as the satellite network. So this is how already people have Ligado has tested with a SkyTerra satellite, which contained a 22-meter diameter reflector to provide the mobile satellite services. So this way, we are also on the direction to moving to 12-meter or 18-meter diameter big antenna on board the satellite, which can provide the seamless mobile services to the user. And as I said, automatically your smartphone gets converted to a satellite phone. Another change which is coming up is the ground station as a service. So now, as I showed you, we have set up dedicated ground station for every satellite, but that will be thing of the past. Now, same ground station can provide service to multiple type of satellite. So that is going to be the trend. So somebody will set up a ground station and it will provide services to whichever satellite wants this services. So the satellite operator don't have to worry about setting up a ground station. So this is the another commercial services change which is coming up in this technology. And these are the different technologies whatever I mentioned is summed up here, that you have a broadband internet, LEO communication, reconfigurable satellite, software defined satellites. So all these things are going to be the technologies of near future. And then there is a talk of what we call universal communication and navigation network, where even lunar navigation or the spacecraft or the space shuttle type of thing, like International Space Station, which are moving in space, they are also getting integrated with the communication system which we develop for the Earth communication, and using optical, lunar, and multi-tier networks. So data relay satellite, our satellites going toward moon, our manned vehicle which are moving as a part of Gaganyaan or International Space Station, or various countries launching their own Gaganyaan system. So all things will be communicating with each other through this universal communication network. So that is going to be another new area which is going to come up. And the ultimate which this particular program uh, showed up on the Polaris recently in September 24. Many of you would have seen about this particular video on YouTube. I'll just I will run it for you. So these four astronauts are on the Dragon spacecraft going across the world, and multiple places in the world they carried out the symphony playing, as you can see, and everything was synchronized together through communication network provided by Starlink. So this is that Polaris mission. So Sarah Gillis is the astronaut who is sitting in the Dragon spacecraft of Elon Musk, and she is playing a guitar. And similarly, people on Los Angeles, some in Uganda, some in Haiti, they are also playing orchestra, and everything gets synchronized through Starlink network. This is in Haiti. And you can imagine the Dragon spacecraft is moving around Earth, and that lady Sarah is sitting in the Dragon, is sitting there and playing the guitar. Everything gets harmonized or synchronized with the orchestra on Earth also at multiple places. So this is how communication is changing. So this was that very popular video which all of you, many of you would have seen. And then ultimately, now we are moving towards what we call the quantum communication. So this is the last topic in this particular communication series. So we started working on this optical or quantum communications with the launch of our GSAT-29 satellites 5 years back, where we launched a optical terminal on board this GSAT-29, and we tried to transmit the camera images through this optical terminal to a optical ground station which was built in Ahmedabad, my place here. in the Space Applications Center campus. So we built this optical ground station, which is different from a RF ground station, which I showed you the first 14-meter big antenna. This is another Earth station setup here in same campus, and it communicated with this GSAT-29 optical terminal was set up. Instead of RF link, now it will have optical link. We are still struggling to establish the communication channel, although we could locate the satellite, we could establish the link between ground station and the satellite, but we are not able to transmit data because of some technical issues which are there on the onboard satellite. So now we cannot repair it also. So we are just trying to see, doing various experiments for ground to satellite, satellite to satellite type of different type of communication data transmission. So this was the precursor, the first development of optical link. And now I will tell you about the Nobel Prize of 2022 in physics went to these three gentlemen, Alan Aspect, John Clauser, and Anton Zeilinger. And they got this Nobel Prize for the work they did in quantum physics, which was done 25 years back. Now you can imagine the work which they did in 1997-98 got rewarded as a Nobel Prize in 2022. So this is the technology whose time has come now, and nobody can stop it. So what will happen is that nowadays you are hearing a lot about cyber fraud happening. Somebody will take away your OTP, somebody will do theft of your password. All these things will be thing of the past, due to which hacking and all these things happen. Uh, that is, the cyber frauds are happening. So instead of, what will happen is that your data will flow through your classical channel, that is the optical fiber network or through RF satellite link, but the OTP or the password will go through the quantum channel. And why it is very safe? Because all the communication happens through the laws of quantum physics, that is using photons of the light for transmitting the password or the OTP. So this is going to be the technology change as far as this type of communication is concerned. And we have already experimented using this. So we are going to launch 2 satellites in low Earth orbit, one in geo orbit, and they will provide the connectivity all across the country. Meanwhile, first we did this experiment in our SEC campus between 2 buildings. Initially, we did it in lab. Then from lab, we moved from one room to another. And then we moved from one building to another. This is our SEC campus. And one building to another building, which are separated by around 300 meters. We transmitted the signal in air, the quantum signal, and it was received at other end. And we used it to send the password, which was used to decrypt the signal, which was encrypted and sent over the normal communication channel. So this is how the first demonstration of free space quantum communication was done in ISRO, that is in SAC in 2020-21. And now we are developing all the technologies for this quantum or optical communication. So these experiments we are still continuing between the buildings, and we are using this optical ground station which will do the communication with the satellite. So for these various technologies and system engineering is being done here at our place. We have set up this optical ground station. It cannot be set up at all the places. See, unlike the normal ground station, which we can set up anywhere in the world or anywhere in India, the optical ground station, we have to study the various sites and then from that select the most appropriate site. So right now we have set up one optical ground station in Ahmedabad. Now another 2 we are going to set up in either Delhi and Hyderabad. So that is the plan, so that we can cover the whole country and provide this type of optical communication and the quantum communication by transmitting the password or the OTP, which will come to your mobile. So this is going to be the technology of future. And in next 10, 15 years, everything will get now operated through the quantum channel. All the secret communication or the passwords or the OTPs, banking transactions, stock market transaction, all will have their passwords, operations will be doing through quantum channel, while the data will flow through the normal channel. So these are all the technologies which we are developing here in Space Application Center, Antariksh Upyog Kendra Ahmedabad, which will help to make our future more and more techno-savvy as well as secure. Now coming to navigation, I will briefly cover this in next 10 minutes. So that navigation, we claim as far as India is concerned that the word, Sanskrit word Navagati or the Sanskrit word now, that itself conveyed that there is navigation. So that was the origin of navigation. That is our claim in India. I don't know the exact truth about this, because many people claim that navigation originated from their place. And why navigation is required? So today I want to locate. Uh, Earlier, when we used to go from one place to another, when you try to locate a new place, say I want to locate this Space Application Center, ISRO Ahmedabad, then mostly we used to ask the panwala to tell you about where is this place located. But today hardly anybody asks the pan galla owner. We just switch on our GPS and try to find out the way ourselves. So the lat long of SAC Ahmedabad is 23.02 north, 72.57 east of this particular place. Then you can locate automatically using your GPS. So that is the navigation trend. And why we are able to do it? Because we will be having at least minimum 3 to 4 satellites, which will provide us this by triangulation, this information related to PVT, or we call it position, navigation, and timing. And the fourth signal is needed. Actually, 3 should be good enough. Fourth is needed to improve the overall accuracy, and because we want timing information also. So working on this direction, India started working in 2000 onwards after the Kargil war. We had our own Gagan system for aiding the aircraft authority, Airport Authority of India for the landing and takeoff of the planes in difficult weather conditions. So that's how Gagan was started, and it was made ready by 2015. And similarly, NavIC was started, as I said, by 2000 time frame after the Kargil war. And now we had all the satellites launched by 2016. Of course, some of the satellites have developed some problem. So now we are replacing them. We are still not nearer to operationalizing the NavIC services, but in next couple of years, you are going to hear a lot about NavIC. I will come to that. And why we are able to locate, because as you can see, many of you are mathematicians and science teachers, so they will understand this theory that by using the signals from these 3 or 4 satellites, you'll be able to pinpoint the location through triangulation, because there are 3 observation and 3 variables. So that way we can find out position and velocity x, y, z, and timing is required. So additionally, we will put 1 more satellite. So 4 satellites are good enough, but if they are bare minimum required, so we generally put more number of satellites. GPS has 32 satellites with 28 operational and 4 as standby, because the satellites are always moving. So some satellites will come into the computational domain and then others will move out of that. So that's why you need large number of satellites. But we have a geostationary navigation constellation. So we need around 7 satellites to cover the almost the whole country. Now, as I mentioned, we started with the initial navigation system called GPS-aided geo-augmented navigation, Gagan. Basically, its aim was to provide accurate services by improving the accuracy of GPS, which is generally of the order of 5 to 10 meters. But what aircraft need, because the pilot needs aiding when he is landing or taking off under the bad weather conditions. So what he needs, he is not much bothered about the very high accuracy. He is more interested in the what we call the integrity of the reading which he gets as a part of the navigation system. So to improve the integrity, we need to augment this GPS system, which what we call the geo-augmented navigation. So we put another 3 satellites in orbit at geostationary location, and they will provide the correction factors for the GPS signal. So that is how the Gagan services were operated. Again, Gagan, in any type of navigation system, it is not sufficient to put only satellites in the orbit. It is also required to have a very elaborate ground segment, which will provide all the measurements so that it can be utilized to provide the correction factors. And there is a need of what we call the user segment, which is carried as a terminal in the aircraft, or as far as navigation or NavIC is concerned, or GPS is concerned, you need a GPS receiver or a NavIC receiver as a part of the user requirement. So this is how the whole navigation scenario will look like. So you have a space segment, you have a ground segment, and you have a user segment, which is the receiver or the mobile, which is the chip goes as a part of your mobile. So this is how the whole system is implemented as far as the Airport Authority of India and ISRO together implemented Gagan. And although it is still not operationalized by Airport Authority of India due to various reasons, but now all new aircrafts are fitted with the Gagan receivers, and the old aircrafts are getting now retrofitted with these Gagan receivers, so that whenever aircraft move from one place to another, and all aircraft movement mostly are all international movement from not only within the country but outside the country also. So the same receiver should seamlessly work with the satellites of India also. They should work with satellite of USA also, of Europe also, of Russia also. So you need to have a universal receiver, what we call a SBAS receiver, which is a part of this aircraft, because any aircraft cannot have 5 or 10 types of receivers for each satellite system. So you need to have a symmetrical, or what we call a unified configuration, which will work with any of the satellite from any country. So that is how this Gagan, or the geo augmented navigation program, has come up, which is called as SBAS, satellite based augmentation system. And we are ready with the implementation. Now only the question of time before all the aircrafts in the world gets fitted with these type of SBAS or the Gagan receivers. And it will aid the pilot in during takeoff and landing, because many times we find that whenever weather is bad in Delhi or Dehradun or some other place, the aircrafts get diverted to safer region like Bombay or Ahmedabad, where weather is not that bad. So every time during winter, our northern region or northeast region face this problem. And similarly, in many countries in Europe, in USA, lot of planes get diverted because of the bad weather conditions. So that will be thing of the past with the introduction of the SBAS receiver, where pilot can even take the risk of landing the aircraft or take off even during the bad weather conditions. So that is the advantage of this type of navigation system. So this is the example of the system which we have developed and implemented in India, that is GSAT 8, 10, and 15. Each contains one transponder of the Gagan payload, and they provide. So actually, only one satellite is needed, but we are active satellites and one standby. So one will work as a standby in space. Two parallel channels will be provided to any receiver working on ground or in aircraft, and that will be utilized to provide the navigation services to the pilot, who will utilize this to go for safe landing. So we have already got certification as far as en route and precision approach is concerned, and now landing and takeoff related these things are pending. Now coming to NavIC, all of you know the origin of NavIC is during the Kargil war, where our soldiers faced a lot of difficulty during the Kargil war. Either the GPS accuracies were very poor. Generally, it is of the order of 5 meter to 10 meter, but it degraded to hundreds of meters or even kilometers. And many times the signal itself were not present. So something was happening in those days during Kargil war. Either it was deliberate or incidentally, but we faced a lot of problems. So government set up a committee which looked into all the aspects and finally suggested that instead of depending on a foreign navigation system like GPS, India should develop its own navigation system, because every developed or every superpower or regional power has its own navigation system. So that way now India is ready with its own IRNSS, Indian Regional Navigation Satellite System. So it is a 7 satellite configuration in L5 and S band with the position and timing accuracy which are similar to what GPS is providing. But only difference is we are having a geostationary satellite configuration, which is more interested in only Indian region. So in and around India and 1500 kilometer around the Indian boundary. So that was the region of our interest. And right now it is the geostationary configuration. So we provide only regional services around India. Our accuracies are similar to what GPS provides. We operate in frequency L5 and S, which is different from what so this is how a typical Indian regional navigation system. So once when we are launching these 7 satellites one after another from 2013 to 16, once Honorable Prime Minister came to Sriharikota to visit one of the launch, and he said in Hindi that we give the very complicated name of IRNSS, Indian Regional Navigation Satellite System. He said in Hindi that आप साइंटिस्ट लोग बहुत ही कॉम्प्लिकेटेड नाम रखते हो, कुछ सिंपल नाम रखिए, नाविक जैसा. उन्होंने तो हिंदी में बोला था, नाविक. but we converted into a English acronym called NAVIC, that is Navigation with Indian Constellation. So you can call NavIC in Hindi also or Sanskrit also. And that's how NavIC name came. So we have 7 satellites. Again, ground segment and user segments are necessary. We made a mistake of not working on user segment or the receiver chip, which goes as a part of your mobile or as a part of any receiver. So we took time in developing that. That's why we got delayed in implementing this NavIC system. But as I mentioned, in next 1 or 2 years, you are going to hear a lot about that, because in between some of our satellite also develop problem due to the atomic clock. Why we are going able to achieve very high accuracy of positioning with this satellite is because we have what we call a atomic clock on board this satellite. So atomic clock is a clock which provides a very stable information, or the stability of that clock is very, very high. It will deviate by 1 second in almost millions of years. Our watch daily, it will drift by few seconds here and there every day. But this atomic clock will provide a rock solid frequency or the clock stability of, as I mentioned, 1 second deviation will happen only in millions of years. So that is the accuracy of these clocks. And that's why we are able to provide 5 or 10 meter sorts of accuracy from a satellite distance of almost 36,000 kilometers. In our case, in case of GPS, it is around 1,000 kilometers. So this is the region of our interest. I already told about that, 1,500 kilometers around that. And we have what we call the one civilian mode, which is usable for everybody, all of us like the civilian people, and other mode is called encrypted services. We call it restricted services, which is available only to Indian military. So same way GPS also has services which are only reserved for the American military, and other services are available to anybody in the world. So this is how a navigation signal will look like, and this innocuous looking signal in L or S band, it contains large amount of information. You will be very surprised to know that this waveform which you see on an oscilloscope or a spectrum analyzer, it contains so much information that it can be utilized to launch missiles, launch anti-missile weaponries, and all sorts of applications we think of. So this is how the activities happen as far as navigation is concerned. So this is the restricted positioning services which I was mentioning for our military user, which is available only for them because it is totally encrypted. Nobody will, other person will not be able to decrypt it. And if you compare, we are the one of the 6 nations in the world. Japan is the 6th one. I have not shown Japan here. So GPS is the American system, GLONASS Russian, Galileo of European Union, Beidou from China, and NavIC from India, QZSS from Japan. So these 6 major countries in the world, they have their own navigation system. So we are proud that India is one of them. Of course, as I mentioned, we are yet to operationalize the system on a regular basis. But as I mentioned, slowly you are going to hear a lot about NavIC in near future. And if you compare, it is almost similar to other countries' services. And as you can see, the symbol of NavIC is also very attractive compared to other countries' symbol. These are the NavIC receiver where we, as I mentioned, initially we were late in implementing. So initial receiver which we built was so big, while now we have a single chip solution as far as NavIC or GPS receiver is concerned. So this is how the technology has changed. And some of you who are familiar with various engineering subjects, they will understand that whatever I have learned as a part of my engineering course in satellite, this electronics and communication engineering from semester 1 to semester 8, that is first year to 4th year. In 4 years, whatever I have learned, all the subjects, everything is part of this small receiver chip, which is used to receive the GNSS or the NavIC or the GPS signal and convert it into position, velocity, and timing information. So you can imagine the complexity of this chip. So this is the GPS or the NavIC receiver chip. So whatever I have learned as a part of my semester 1 to 8, whether it is antenna, it is RF microwaves or microprocessor or digital signal processor or power supply, everything is contained in this small chip. So you can imagine the capability of the what we call the supercomputing capability of this particular GNSS receiver chip. And that is where we made initial mistake of not going for this chip development on our own. And because the GPS chips are not usable for other system, there was the advantage that GLONASS or Beidou or Galileo system of other countries, they can easily use GPS signal because GPS chips because the signals were similar. But in our case, the signals were in totally different frequency band. So we have to ab initio design our antenna system, we have to design our RF system and the processing system. Everything we have to do on our own. And that's why it took time to put that receiver chip into the mobiles. Now these mobiles which I have listed, Xiaomi M18, Mi9, V20 of Honor, Oppo 10X Zoom, Lenovo 26, all this now contain NavIC. And there is a rule in countries like Russia and China that if you are in that country, you have to necessarily use their navigation system. Unlike that, in India, we have not made that rule, but tomorrow it may come also anytime. Once we are operationalizing our NavIC system, so you can use GPS, but in Russia or China also. But your mobile has to be Beidou enabled or GLONASS enabled. Similarly, our mobile in India should be NavIC enabled. That is going to come in future. So we tested this our receivers all across the country, different places. Even we provided it to our military people also. They tested it everywhere, and you can see the results. We are achieving a very consistent result all across the country, and we are second to none to even GPS. Our services are equally comparable to what GPS is providing. And similarly, for military also, we have built the receivers as the initial prototype, and finally it will be handed over to the corresponding industries for developing military grade receivers. So we have come out with the ICD or the what we call the interface control document. So anybody in the world can build the receivers for GPS or NavIC or GLONASS or any navigation system. So this is for civilian services, which are open services. So this anybody can utilize these services and make it. We have got certification for vehicle tracking, AIS 140 standard, maritime, civil aviation, UAVs, telecom, Authority of India, then course. Data formats are also compatible to international standards of NMEA remix. Differential GNSS is used to provide centimeter or millimeter level of services for various very critical applications and safety of life services also. And now we have introduced L1 signals so that our signals are also now compatible with GPS signals. So I can use now GPS chip to develop my L1 band NavIC receiver also. So that is the change which is coming up in recent years. And all these things have been already implemented. And it is a very short period. You are going to hear a lot about NavIC. The usage of NavIC, as you can, if you compare as a commercial business also, there is a lot of scope for anybody who wants to do business in NavIC receivers. So as you can see, all type of, you must be very surprised to know that when you wake up in the morning and sleep at night, within that time period, almost 90% of activity which we do are influenced or governed or controlled or in some way they are influenced by navigation system. And by navigation system all across the world, almost 90% of navigation happen through GPS signal. So you are governed indirectly by GPS that we don't know, but we are governed that way or influenced in some way or the other by GPS. So instead of that, we urge you that we should be governed by our own country system, that is NavIC. So as you can see, it has applications almost everywhere, all type of transportation, all type of even research also, remote sensing related research, and of course, military has maximum usage of this navigation system, whether it is marine, aeronautical, terrestrial, UAVs, aerial weapons, gun, mortar, launcher, and short-range weapon system, precision timing information, synchronized networks. So as you can see, lot of civilian applications in e-governance we have been using, whether it is vehicle location, safety of life alerts, SACET, then real-time train information. All our Rajdhani and Shatabdi trains have been installed with this NavIC Gagan terminals. Swamitva mission of our Ministry of Urban Areas. Then similarly, Aadhaar card is now linked with the the Aadhaar enrollment services. Wherever we get the services, they are location-based services which are stamped with the NavIC location. Similarly, all type of activity for traceability of time in the country is now timing is synchronized. Indian standard time is synchronized with the NavIC timing. So like that, for security also, it has been used in a big way. So as you can see, NavIC and mobile is the ultimate, which many phones have already started giving these services. But it is just a question of time when all of our phones will have, even feature phone will have this feature of NavIC enabled services. So this is how we are going to use NavIC even for the, there is an idea about the using it as our electronic voting machine also, so that nobody can do any tampering with the EVM machine, our other location machine, and all these things have been going on. And as I mentioned, we are regularly monitoring the movement of all the Indian railway system, all locomotives, through the combination of navigation and communication. That is our mobile satellite GSAT-6 services. So we call it NavCom, or the Prasasnik Upyog governance applications. So whether it is movement of fishermen in the oceans, or the movement of trains on the railway tracks, or the movement of aircraft, especially Indian Air Force is now going to use in a big way. All the transport and the fighter aircraft will contain this real-time aircraft tracking system, which is based on NavIC, Gagan, as well as the GSAT-6 mobile satellite services. So combination of navigation and communication, they provide services. All our earth station, whether it is Strak, MCF Hassan, Sri Harikota, from where we launch our satellite, everything is now linked or controlled or synchronized with the timing which is provided by NavIC. That is the 1 PPS signal and 10 megahertz clock. So all our stations are synchronized with that. All our timings all across the country is synchronized with the NavIC timing. IRTCT Railways, CRIS, Center, that is the Center for Railway Information System in New Delhi, Chanakyapuri, all are getting synchronized with that. You can also synchronize your computers or mobile with the NavIC timing. You just have to log on to our SEC's website and get the NavIC timing and synchronize your network with the NavIC time. We have also synchronized it for the our what we call the electric grid system, because when war happens, the first thing enemy will attack is your power grids, because if you disrupt the power supply in the country, everything get disrupted. So we that is all synchronized with GPS right now. So instead of GPS now, we are slowly converting or shifting to NavIC based power grid synchronization. So we tested it with many of the power grid stations, and it is giving exactly same result as GPS synchronization. So that is going to be the norm now everywhere. We will be converting. Somebody wrote to Prime Minister that in Siachen our soldiers died, and India is claiming to be a world leader in space with lot of communication navigation system, but we are not able to locate the bodies of our soldiers who die in avalanche or snowstorm on Siachen. So why not we do something for that? So we started working on that. We are coming up with a wearable type of watch type of unit, which will work both as a navigation as well as communication tool. So the movement of the soldiers who go there for 3 to 6 months, their movement will be tracked continuously using this wearable unit through the NavIC signal and the satellite communication. So sitting in Srinagar or in New Delhi, we will keep track of the movement of our battalions on the Siachen Glacier. Similarly, NavIC in mobile is going to be the ultimate, as I mentioned. Within next couple of years, we are going to hear a lot about that. NavIC, RS, or the restricted services receivers for our strategic sectors have been already undergoing implementation, and it is a matter of time where all our armed forces will shift to NavIC-based systems, because military is the biggest user of navigation system. Even for going to moon or any other planet also, now we are developing what we call a space service volume GNSS receiver, which will, you'll be surprised to know that we are receiving GPS, NavIC, or Beidou, or all type of navigation systems which are on Earth that signals. The backlog of that is received when we are going towards moon or going towards Mars also. So that can be utilized to do navigation or even landing on moon or Mars. That also it can be attempted. Similarly, we have developed our own pseudo-light system that is called a navigation system. Instead of a satellite-based navigation system, a satellite-based pseudo-satellite-based system, or it is called a satellite on ground, where we set up a local satellite system on ground, which will help the plane in landing in a difficult terrain situation. So you can set up a localized navigation system in a difficult terrain, like where mountains are there or very hilly terrains are there, we can set up our own locating this type of navigation system. It is called a pseudo satellite. So satellite on ground, it can be utilized for a temporary landing of such aircraft system during wartime or any of the system. So these are going to be the new areas of working as far as navigation is concerned, real-time kinematics, precision point positioning, where you can achieve centimeter to millimeter level of accuracies of positioning instead of 5 or 10 meter. So that is how the world is changing. For government services, we can do message authentication because navigation services are prone to what you call spoofing and jamming. Jamming means somebody can transmit a L band or S band signal and jam your signal, and you will not get the positioning, and that has happened at a lot of places, especially during wartime. The enemy will jam your signal. Similarly, to take care of such critical services, we do what we call message authentication, because somebody can misguide you. So missile, instead of landing on your enemy, it will land in our surface itself, on our boundary itself. So you can spoof or fool the navigation system. So that sort of things are also happening. So we have to take care of this type of anti-jamming or anti-spoofing measures also. And as I mentioned, when we are going to interplanetary services, so space service volume receiver, which will be utilized to do guiding, navigation and control when we are going towards moon or landing on moon. So that sort of things are also possible. Now, as I mentioned, we are already talking of geo and MEO type of communication, navigation, but now Starlink type of satellite will also be possible to use for what we call LEO PNT. So because these satellites are moving satellites, there will be a Doppler frequency, and that can be utilized to fix the position on ground. And similarly, you can carry a small navigation transmitter on board these satellites to do transmission instead of GEO or MEO satellite. So this type of newer navigation systems are also emerging, and even private sector is now coming into the place. And there is through these companies, Zona Space Systems and Trust Point, they have come up with their own LEO PNT systems where they will launch large number of satellites which will provide navigation services like GPS using the LEO satellites. So, and as I said, the atomic clock is going to be the major building block of any navigation satellite, which has a stability of millions of years. So that is how the we have invested in that development also, and I'm proud to say that in SAC we have built the our indigenous atomic clock, which is being utilized for all our now future satellites. And then navigation will also be is going to be used. All of you have heard about FASTag, which has revolutionized the toll tax at the roads. Now, instead of FASTag-based electronic tolling system, we are now working on what we call a navigation-based or NavIC-based e-toll system. So where automatically you don't have to worry about to carrying the FASTag and all. Your amount of the time you use the highway or the expressway, automatically it will be logged using your navigation receiver, and your amount will be deducted for the time you are on the highway or the expressway. Similarly, the railway accidents which are happening due to the train entering the wrong track, and we hear of some of such accidents in India and many other countries. So that will be thing of the past with this Kavach indigenous automatic train protection system, where we can use the spacing between the two tracks that can be monitored using the navigation system, and that can be utilized. So a centimeter or millimeter level sort of accuracy will be needed, or I can use a differential GNSS system to implement this automatic train protection system so that the train will not enter the other track. There are various scientific application also, and remote sensing is one of them where we can utilize this navigation signal to do the remote sensing. So instead of launching a dedicated remote sensing satellite like radars or optical camera system, we can use the navigation signal which are anyway there. The reflected signal can be collected by the receiver on board any LEO satellite, and we can do a lot of analysis and implement for application like soil moisture or vegetation detection, sea ice monitoring, snow monitoring, all these things. So we have already done this experiment by launching a microsatellite with this GNSS payload and retrieved the soil moisture, the surface inundation, wind speed, and significant wave height. So these are some of the satellites which are already operational all over the world: Cygnus, 3Cat2, GEROS, Paris IOD, and Microsat 2C, which is our own Indian satellite. So this is another area of research as far as scientists are concerned. So lunar PNT, where on moon we'll use navigation system, we launch satellite around moon, which will provide, like GPS is providing or NavIC is providing services on Earth. Similarly, there will be dedicated navigation satellite providing services on moon. Similarly, we have now LEO constellations are already going to happen through private sector, and underwater navigation for submarines and many other underwater vehicles will also be required for use for many military purposes. And this is what lunar PNT is, what I was mentioning, that we'll use the backlog of the Earth system like NavIC or GPS to find out the position of the spacecraft while it is going toward moon or toward Mars, or we can use the dedicated satellite around the moon, which will be, each country will launch one satellite. So NASA will launch one, Europeans will launch one, Japanese Space Agency will launch one, India will launch one satellite. So like that, we'll have 4 or 5 satellites around moon, which will provide the navigation services, and they will be all similar in nature, so that there will be a unified synchronization between this satellite launched by each of this country, and that will be used to do navigation, especially the navigation on moon, because when we want to land on moon, and especially when in future we want to set up colonies or put men on moon, that time this type of system is going to be very good. It is called LunaNet or lunar PNT network, which is going to be the thing of the future, navigation for future interplanetary services. And finally, AI/ML in space, we have been using it in some way or the other: remote sensing or interplanetary mission, communication, autonomous spacecraft health monitoring, fault detection. So this is a typical application in satellite communication, where signal identification, automatic resource allocation on board the satellite, like power or the bandwidth, traffic modeling or forecasting, beam hopping pattern, beam forming, all these things we are using AI and ML techniques for implementing that. And lastly, Gaganyaan program, which we are doing, where we are going to put man in space, and the Axiom 4 mission is going to happen tomorrow, where on 10th June, one of our astronauts, Vanshu Shukla, will be going on the Axiom 4 Dragon spacecraft toward the International Space Station, and he will land up in the International Space Station and interact with some of us on ground here in India. So, and before we put our own men in space through our own Gaganyaan, so the activities are going on in full swing. So we have everything, almost: launch vehicle, satellite, the crew cabin, the parachutes, and the space suit which are needed. These 4 Force pilots, test pilots have been already identified. Supanshu Sukla is one of them, who is going to go to International Space Station tomorrow. And we have our own Gaganyaan mission, which will be there for minimum 1 to maximum 7 days. It will be at the orbit of around 400 kilometers. And the one major requirement why I have taken up this topic is because 100% true communication, that is a must requirement for any manned mission. So for no single minute, we don't keep the astronaut away from us. They will always remain in communication with us on Earth. Right now, with whatever resources India has, we are able to have only 40% of time this communication. So from 40%, we have to bring it to 100%. So we have to launch another 2 geostationary satellite, which will, because Gaganyaan will be moving over India only 2 times in the morning, 2 times in the evening. Rest of the time it is moving somewhere else in the world. So that time it will remain in contact through this geostationary satellite to our Bangalore center, from where we will continuously be monitoring the movement of the Gaganyaan, as well as the communication with the astronaut will be continuously provided. 3 astronauts can sit in our crew cabin, minimum 1, maximum 3, and it is going to be launched from Sriharikota, and it will re-enter and land back, or descent will happen, re-entry will happen, and final landing will happen near Andaman Nicobar. That is the place right now we have zeroed down, but it could be at any other place also in future. That will be done. And finally, the Bharatiya Avkash Station, like International Space Station, we have planned to, by 2028, we'll launch the first module, and one after another 4 modules will be launched. So by 2035, we'll be completing the integration of the total Bharatiya Antariksh Station, what we call it BAS, and we'll do various experiment like it is being done on International Space Station. Tomorrow, Subhanshu Shukla will be there on ISS and he will be doing almost 30, 40 experiments of microgravity related thing. There are totally 4 astronauts going on this Axiom 4 mission. So same way in future, we will have our own mission to Bharatiya Antariksh Station. It will be also used as a transit point for putting man on moon. Modi Saab has already announced, our Honorable Prime Minister, that we will be putting an Indian on moon by 2040. So we are all on the way working towards that goal. Of course, it is easier said than done. So it is very difficult task. All of you can understand that. But if we have such a Bharatiya Antariksh Station as a transit, then it makes our task easier. So this is going to be the another area where we'll be working. And future, which we are talking of, space tourism, space station, quantum communication, space colony being set up on Moon and Mars. So all this will need communication and navigation as two major essential elements if you want to achieve all these things. Space tourism has already started in US and Russia. Similarly, we are going to launch our own space station. So it is not far off that things which right now look very distant are going to be in very near future. It will be going to be a reality. SEC, we work on remote sensing, navigation, communication, space science and technology. Of course, outreach training, we have a very good exhibition and all these things. So I urge you, all of you, whenever you visit Ahmedabad, please do come to SEC, visit our exhibition, visit our center and look yourself about the various activity which are happening here. So thank you all. Questions are there. If you are still not bored enough, please let me know. You can answer them. Thank you.
Thank you. Thank you very